Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do a access symmetry problem. Now what particular example you are seeing on my screen is interference or shrink fit. We have done this type of example in past. We have one example, but we are going to do this example using access symmetry element. So you see there is a interference between outer bushing and shaft, and then that interference over a period of time is removed, and then we are going to check how the stresses is generated within the shaft and bushing, and what particular contact pressure is required for this type of interference fit. This is exact problem we are going to do now. This will be a combination of interference fit plus access symmetry problem. Now in past we had done contact interference fit in Abaqus standard, but this we had done for a quarter symmetry. It was not access symmetry, but it is quarter symmetry. We assume shaft as rigid and with linear property. So today's problem we are going to do with a deformable shaft and the deformable brass bushing. Also we would recommend you to go through our the one of the video on the access symmetry stress element where we have done a Brinell hardness test. So we recommend you to go through this, so you will get a fair bit of idea how to do a access symmetry analysis, and you will be more empowered to do this example. So in today's problem we'll just define a problem, what is a problem, and then we'll start modeling it. So today we are going to do a interference or shrink fit simulation in Abaqus standard using use of access symmetry element. We are going to use mainly CAX4R. So it is a 4-noded bilinear access symmetry quadrilateral. R stand for a reduced integration, and you have different hourglass control. Now interference fit, also known as a press fit or the friction fit, and it is a method to fasten between the two parts which achieved by the friction. Now these are the old mechanical fastening techniques. Still with so many years of invention of interference fit, still also in industry, bearing, shaft, bushing, all those things, joints are done using this interference fitting. Now for metal parts in particular, the friction that holds the parts together is often mainly greatly increased by the compression of one part against the other. So mainly you have compression and the friction between the two mating parts that driving this fastening quality. Also this friction and the compression between two parts are mainly depend on the compressive strength and tensile strength. So for you it's very important to really check what is the stress developed within the parts, bushing, shaft. Typical examples of the interference fits are the shaft of the bearing houses, then you have cable connectors. There are so many in today's mechanical world, and it's an old fastening method. Today's problem, what we are going to do, we are going to have a solid shaft which will be 100 millimeter in length. There is a typo, this is a 200 millimeter in length. Diameter will be 50 millimeters. We are going to use steel property. And then we'll have bushing length 50 millimeter, ID is lower. So if you see, bushing ID is 49 versus shaft diameter 50. So you almost have a 0.5 millimeter circumferential interference fit. So circumferential we have interference fit. Now this particular example is bonded shrink fit, where actually temperature is increased. We are not going to do this. So we can do this also if you have temperature dependent property. We are not going to do it. So we are going to have a blue color steel shaft. Over that we are going to do bushing. Now as soon as you see this problem, you can immediately see we can do it using access symmetry. So it's straight away it's access symmetry problem. So if I take an axis along this, you can model this access symmetry problem. So you don't have to do a full solid 3D element, then it's your computational time is high, and then you have to get a boundary condition, stability, convergence issue. So quickly we can do it access symmetry. Secondly, it is also symmetric about the y-axis, so you can use a symmetry boundary condition here. So we can just put one quarter axis symmetry and directly use that for our modeling. So it will be quick, fast, and then we can able to generate a data with fine mesh. You can find what is the stresses generated, contact pressure, so many things you can do. Now typical property what we have taken brass is 100 GPa. We are going to use ton millimeter Newton second, so this will be in MPa. So 100 kMPa, Poisson's ratio 0.3, 80 is the yield stress for 0 plastic strain, 120 for 30% plastic strain. Steel is typical 210 GPa, 210 e power 03 MPa, then you have 180 for a yield stress and 240 as a 0.3. There are a lot of packages available worldwide. A lot of people use these packages and they want to get this answer, what should be the interference value when they put a joint, what is the contact pressure, what is the tangential stresses develop on the shafts, and this package is also very costly. You can use a simple Abaqus axis symmetry model, and you can build DOE, design of experiment, or generate a lot of data to find all this answer accurately. So that's what actually we are going to do. So the other learning what we'll have is how to model interference. So this is important learning out of this problem. You will able to model how we can model interference fit. In interference fit, you have to first define a proper contact before the step, and in step you have to define the interference fit. This is the important step, and this is a key takeaway game for this type of problem. So the two key takeaway, one is the axis symmetry element and another is the interference fit. That's what actual learning you'll get. So let's start a problem. So let me clear this. So let me first set the working directory. Let me go to Abaqus Acumen. So I set the working directory. Now first thing, we'll quickly build shaft. We give on a shaft, it will be axis symmetry, shell deformable, approximate side 300 I put. We are going to put a quarter symmetry, axis symmetry model with quarter symmetry. So I'm going to put 0, 0. So I get a origin point. One important takeaway when you solve this problem, your model should be in a first quadrant. Your model cannot be in second or third or fourth quadrant. As soon as you put a model in second, third, fourth quadrant, it will not able to solve. The number one requirement from Abaqus is a model should be in the first quadrant. So you should have everything is a positive X and positive Y. You should not go to the second, third and fourth quadrant. Now shaft outer diameter is 50 millimeter. It's a solid shaft, so only one diameter. So this is, I just put 25 radius, and then total length is 200, but we are going to put a Y symmetry. So I'm going to put only 100. So I'll put 25, 100. So that way I got the other point, and then I'll put 0, 100. So I get this point. I generally put a point just for a reference to find where, or you can just put a. So we have done this, and then you say okay. So we are done shaft. Now when we have to, the other important thing whenever you look problem is the bushing total vertical length is 50 millimeters. So it is going to have a 25 millimeters. So I need to cut this shaft. Otherwise, defining a contact, I would select the full surface. So I'll better cut it. Now for cutting, we'll just use a datum plane and we'll cut it, not to exact 25. So if you have 25 and 25 both at the same length contact, then you get a contact chattering. So I'm going to put a 30. So let me put datum plane. I want to have this perpendicular to this, so it will be XZ plane, and I'm going to this offset by 30. So I got a plane here. Now I'm going to quickly cut it. So I cut it face using datum plane, and I'm just selected datum plane trim. So I got a trim part. This will be easy for me to select a master surface. So master surface will be which one will have a stiffer. So steel is stiffer than brass, so the stiffer will be the master surface. Now we'll create a property. It will be typical steel property. We are going to put elasticity, Poisson's ratio as 0.3. Then we put a plasticity data. It will be 180 as a yield, and at 240 we have 30% strain. Let me go to the PPT and just confirm it. Yes, we have put right property. You can have a complete stress strain curve also. This is just tutorial example, so we just taken 2 points. Then it will be shaft, solid shaft. So it will be a 3D. So even though it's axis symmetry, but it will have a 3-dimensional problem. So it will be 3D problem. So you have to select a solid homogeneous shaft, and then metal property steel. You have done it. So if you have plane stress, plane strain, you have to select it. But for axis symmetry, you don't have to select this. Then you go and assign this section to the shaft, and that's we are done. Now we are done with shaft. Now let me create brass bushing. It will be deformable axis symmetry 300. Now this will be again I create a center point 0.0. The inner diameter will be 20 diameter will be 49. So radius is 24.5, and then outer diameter will be 50, 0. The total length is 50 millimeter, but since we are putting a symmetry about y, so it will be 25. So 24.5, we'll have 25, and then 50, 25. So I just put this. So we're done with brass. Now let's create the property for brass. It will be 100 mpm modulus and 0.35 Poisson's ratio, and then we have plasticity data. It will be 80 as a yield, and then let me check what is a 120 as the MPa at 30% strain. We done that. We'll quickly create bushing. It will be solid homogeneous. We're going to select brass, no plane stress selection, so it will be solid because it is just 3D. It is solid element, but only you are reducing the problem 3D problem to 2D. Then we'll assign this to bushing, and that's it. We have created both the part, everything we have created. We'll put instance will create. So once we have created instance in assembly, you can see there are interference. So there is a circumferential interference. Now we'll put mesh. So mesh you cannot do in assembly, you have to do in part. So bushing, we are going to use medial axis theorem, which is good for this type of part. We'll just check whether we have selected the right element. So it's perfect element, 4-noded bilinear axis symmetry element CAX4R, and then we'll just put seed, not 2 millimeter, we'll put 1 millimeter. This is the advantage with axis symmetry or symmetry modeling. You can go with a fine mesh which give you better results. If in case you have to put all solid mesh, you maintain an aspect ratio, the computational time is high, you cannot do very better mesh with this. So and then we'll mesh it. So we're done meshing. Now for shaft also we'll use same theorem. the shading which we are going to go to 1.2, bit coarse compared to the bushing. It's a master surface. So we created both. You can see in parts instance, so you can see clear cut there is interference. Now what we'll do now, to have a contact definition, we have to create a surface. So for shaft we'll create master surface. So we're done with master, and then we'll create for this symmetry the bottom node set. So set will say create nodes Y symmetry shaft. So we can select it. So we have selected that. Similar we'll create for bushing. For bushing also we'll create slave surface, and we'll select the inner slave surface. Then we'll create a node set for bushing symmetry Y. One minute, bushing symmetry Y, and then let me first select it. So now we are almost done most of the part. We have generated the part definition. We generated two surface for a contact. For boundary condition we put everything here. So let's go to the interaction property, create a frictional property. So since the friction tangential behavior, we are going to put 0.3 as a friction, 0.2 as a friction, because brass will be very smooth and soft material, so friction will be on lower side. 0 is frictionless, 1 is a sticking condition, so we are going to put 2. Again, for this type of problem you can also do a design of experiment for a different friction value, how the contact pressure or stress is going to generate. We'll create surface to surface contact using standard. Let me put some name. And now we are going to select the master surface. So master surface will be on shaft, and the slave surface will be on the bushing side. So we have defined a contact between this and this. Now this is all regular normal stuff. Now we'll put boundary condition. Boundary condition will be having on shaft, which will be the shaft node will be having symmetry boundary condition for Y symmetry. And then you have Y symmetry. Even though it's a Y symmetry U2 X rotation and Z rotation, actual for axis symmetry element only you have 3 degree of freedom, R, theta, Z. So vertical displacement, which is Y, radial displacement and theta, that's what you have. So you are vertically your constraint. You'll create for bushing. You go for bushing and then select bushing node and then put Y symmetry for bushing. So you put boundary condition, there is no load. Load itself is this contact interference. So we are going to put a step. You are going to say interference feet. Static general, you are going to do NL jump on. Put some stabilization, initial stabilization, because vertically you are constrained, but radially it is still free. Theta you don't have to worry. And then you put enter interference feet as the name. Increment start with very initial increment 0.001. This is the key, guys. Initial increment should be very slow for this type of analysis. Now and then 1000 will be sufficient. So we created the step, and then shall we run it now? No, there is a key. Now I'll just go to the PPT. In Abaqus, we had to first define a contact everything. Once you define a contact for interference definition, it will be contact interference definition. So this is a general contact what we are define, but this contact is an interference contact that you have to define in step, not before the step. So that's the where actually we are still defined. So right now ours is contact pair, we are defined friction, surface to surface, this is defined, but we need to convert this contact into a interference contact interference shrink fit we have to convert. So that will do it. Now once you've done that, again go to, this is key, guys, you go to the interaction, you go to contact and you say edit. Once you say edit, now this option will open, interference fit. This option will not open unless you define a step, and here you say interference. Now no allowance interference, your different option. We can have different video on this, how we can do. Then gradually remove the slave node organ difference. Automatic shrink fit, what we are going to use. Uniform, we can have different option, but we are going to use automatic shrink fit. That's what actually we are done. Okay, now we can create a job, interference fit. We'll do data check. Data check is a good option, so you can find if there is any pre-processor related issue. So while data check is going on, I just want to show you something important. I'll also save this file. So data check is done, and let me save this file. Now in TextPad, I just want to show something to you, how the deck look like. Even though we do a lot of from Abaqus CA, I recommend use a TextPad. That way you can become familiar with commands. So you define surface property, friction you define, a contact pair. So this is a typical contact pair what we define. You define a contact pair. Now this contact pair is converted into a contact interference or shrink fit here within step. Now the deck is ready, so let's run it, see what results we get. So we submit it, just wait for the results, and then once results it out, we can have discussions. So guys, run is completed, results are out. I think it's I'll also remove this the mirror pattern, which was mirror pattern, everything was on. So this is what exactly the problem look like. So this is the stress generated. So you see now how the interference is removed. So interference is removed over a period of time, and this is a stress pattern generated. Now the other learning what you'll get is you can make it a 3D solid model out of it. So you go here and then first you put this axis symmetry, so that way you get a full length model, and then you put a swap 180 or you can have 360. 180 just to get inside how the core is getting stress and how the outer bushing is getting stress. So that way you can get understanding how the stress pattern is generated. Now other important thing is you can look into different parameter along with stress. We can also look for how is the contact pressure. Contact pressure is also important, how the contact pressure is getting applied. So let me first remove the bearing. So this is for shaft. So pressure you see in the middle, it's gone to 70 MPa, and then we just have contact till 25. So 25 to 30 there is no pressure generated, and this is the pressure gradient. Overall you see pressure is around 70 MPa, that is the pressure generated on this. So let's look into bushing will put on and shaft will remove it, how it looks here. So similar pressure is, opposite pressure is also generated here, similar pattern 70. So this is the few answer. You can get number of answer what you want, but our main objective today's video was empower Abaqus user with access symmetry element, empower them to the interference fit analysis. That's what actually we want to give, and that's we are demonstrated in front of you. So in case you like this video, don't forget to like us, subscribe us. We need your support to take this project forward. So thank you, bye bye.